Dear students, in the previous class we discussed about the elements of symmetry. That is the elements of symmetry. In that we have discussed about the plane of symmetry, then axis of symmetry and center of symmetry we have discussed in the previous class. In this class we are going to be discussing about the fundamental condition for the optical isomerism. In the above video we know that what is meant by symmetric molecule. Symmetric molecule means the molecule which is having all three elements of symmetry is called as a symmetric molecule. Then asymmetric molecule means the molecule does not have any elements of symmetry is called as a asymmetric molecule. Then the disymmetric molecules means the molecule does not having the plane of symmetry is called as a disymmetric molecule. This we are discussed in the previous class itself. Now, the fundamental condition for the optical isomerism means the presence of the disymmetry. That is, fundamental condition for the optical isomerism means the presence of disymmetry in the molecule. Disymmetry in the molecule. This is the main fundamental condition to a molecule to exhibit a optical isomerism. To exhibit a optical isomerism means absence of plane of symmetry. The molecule is going to be exhibited. The molecule is going to be exhibited optical isomerism. Optical isomerism. Now we are going to be discussing about the how to calculate the number of enantiomers is going to be exhibiting by a molecule. Means to calculate the number of enantiomers is going to be exhibited by the molecule by using the formula that is going to be 2 to the power of n. 2 to the power of n. Here the n is nothing but number of chiral carbons. Number of chiral carbons. Suppose the molecule contains n is equal to 1. If the molecule containing that is 1 chiral carbon, that is going to be exhibiting a 2 enantiomers. 2 enantiomers. If the molecule containing that is n is equal to 2. N is equal to 2. At that time, the molecule is going to be exhibiting that 2 square is that is a 4 enantiomers. That is going to be 4 enantiomers. Like this, we are going to be calculating the number of enantiomers can exhibit by a molecule. Number of enantiomers can exhibit by a molecule by using this formula. By using the 2 to the power of n. This formula. By using this formula, we can calculate the number of enantiomers exhibited by a molecule. Certain compounds, if you are going to be taken certain compounds that is contain the more than 2 chiral carbon atoms also, that is optically inactive. Why? We will take some example. That is mesotartaric acid. We will take the example mesotartaric acid. That is, if you are going to be taken the mesotartaric acid, this is the mesotartaric acid. This compound contains the 2 chiral carbons. You can observe that. We know that what is meant by chiral carbon. Chiral carbon means the carbon which is surrounded by the 4 different groups that we call as a chiral carbon. In this, you can find the 2 chiral carbons in this compound. Then it's going to be exhibits the plane of symmetry. That is the plane of symmetry. This exactly plane of symmetry means the imaginary line drawn through the molecule is going to be cut into 2 halves. That is going to be exactly the same. Means this having that plane of symmetry. That is the plane of symmetry. Means it is having the plane of symmetry. Therefore, this molecule does not exhibit the that is optical activity. Does not show the optical activity. This molecule is optically inactive. Because the optical rotation produced by the upper chiral carbon atom. This carbon atom, upper chiral carbon atom, is going to be cancelled by the rotation, that is the optical rotation of the lower chiral carbon atom. Therefore, this we called as an internal compensation. Therefore, this molecule, if it contains the more than one chiral carbon atom also, it does not exhibit the optical isomerism. Means this molecule is optically inactive. We'll take some other example. If you are going to be taken some other example. Name of this compound we are going to be taken as that is the name of this compound we are going to be taken as that is 6,6 dinitro diphenyl, that is 2,2 that is dioic acid. In this, you can see that, you can observe that is this compound does not contain any chiral carbon. This compound does not contain any chiral carbon, even though this is going to be this molecule is going to be optically active. Means certain, from this we can say that there is some of the compounds. The fundamental concept for this to exhibit the optical isomerism is the absence of, that is the absence of plane of symmetry. We can say that. Otherwise, we can say that presence of dissymmetry in the molecule is the fundamental condition for the that is the optical isomerism. In this, this about the fundamental concepts for the fundamental condition for the optical isomerism. Now we are going to be discussing about the some other terms related to this optical isomerism and all. Then now we are going to be discussing about the diastereoisomers. That is diastereoisomers. What is meant by diastereoisomers? This diastereoisomers means a pair of stereoisomers. These are not related as object and mirror images. These are not related as object and mirror images are called as a diastereomers. Means a pair of stereoisomers is not related as object and mirror images is called as a diastereomers. Example for this, we are going to be taken that mesotartaric acid and the dextrotartaric acid. We are going to be taken the mesotartaric acid. Mesotartaric acid, already we know that. So many times we have written this. This about the mesotartaric acid. This mesotartaric acid and that is dextrotartaric acid. That is dextrotartaric acid means we can be written as COOH, then COH, H, COH, H, and COH. These two are, this is the pair of stereoisomers. A pair of stereoisomers does not related as object and mirror. You can see that. You are finding any object and mirror image relation between these two. We are not finding. Therefore, this we called as this pair of stereoisomers we called as diastereoisomers. Diastereoisomers means does not related as an object and mirror images, that we call as a diastereoisomers. Then next we are going to discussing about the mesoisomers. That is mesoisomers. That is mesoisomers means the compounds are optically inactive. The compound of the stereoisomer are optically inactive in spite of presence of the chiral carbon atoms also. In spite of the presence of the chiral carbon atom means the presence of chiral carbon atom also is optically inactive. That type of compounds we call as a mesocompounds. That we call as a mesocompounds. That we call as a mesocompounds. Mesocompounds means we are going to be taken that is take that the mesotartaric acid. This we are going to be taken that mesotartaric acid. Even though the presence of chiral carbon atoms, this compound is optically inactive because that is optical rotation of the upper carbon atom is going to be cancelled by the optical rotation of the lower carbon. Therefore, this is due to the internal compensation. The internal compensation means the rotation of the that is optical rotation of the upper carbon is going to be cancelled by the optical rotation of the lower carbon is called as an internal compensation. This we are going to find in this compound. This compound we call as a mesocompound. Then next we are going to be discussing about the racemization. That is racemization. What is meant by racemization? This is so many times asked in the examination for the 1 mark. That is the process of conversion of optically active isomers into optically inactive racemic mixture is called as a racemization. Means the optically active isomers means that is dextroisomer and levoisomer into conversion of, that is going to be conversion of, that is into racemic mixture. Here these are optically active. But these are optically inactive. This is optically inactive. This process we call as a racemization. Racemization means the process of conversion of optically active isomers The process of conversion of optically active isomers into optically inactive racemic mixture. Optically inactive racemic mixture is called as a racemization. Is called as a racemization. So many times asked in the examination. This is one for the 1 marker. Then next we are going to be discussing about the resolution. What is meant by resolution? Here the resolution means this is the process of separation. Here the process of separation of optically inactive racemic mixture into optically active isomers. Optically active isomers, that is dextroisomer and levoisomer, is called as a resolution. That is the reverse process, just racemic mixture. Separation of racemic mixture, that is separation of racemic mixture, that is separation of optically active racemic mixture, the optically inactive racemic mixture, that is separation of this optically inactive racemic mixture is going to be separating as the optically active isomers, that is the dextroisomers and levoisomer. These are optically active. These are optically active. Means here the process of separation of optically inactive racemic mixture into optically active isomers is called as a resolution. Is called as a resolution. Now we will discuss about the retention in configuration. Retention in configuration means during the reaction, if the product having the same configuration of groups around the stereogenic carbon atom as that of the reactant, is called as a retention in configuration. Is called as a retention in configuration. We will be see one example. That is the carbon. Suppose this is a carbon having that. There is a A. This A, B, C. This is about the X. We will take that. That is the living group. We will take the living group. This it's going to be attached with the nucleophile. It's going to be attached with the nucleophile. We are going to be get that product. A, C, B. Here that is a 1. Means instead of this is going to be replaced by the Y. X is going to be replaced by the Y. But the remaining group of atoms, having the same configuration as that of the reactant. You can see that this type of configuration we called as a retention in configuration. This we can find in the SN1 reaction. But inversion in configuration. When it comes to that inversion in configuration, means the name itself is going to be say that the meaning of this inversion in configuration means opposite. Means during the reaction, the product having the opposite configuration of groups of atoms around a stereogenic carbon atom in the reactant, as that of the reactant, is called as a inversion in configuration. You can see that the same we are going to be taken that C and take the stereogenic carbon. This is the stereogenic carbon. This is the A, C, B and X. This is about the 4 groups which is attached to the stereogenic carbon. then it's going to be attach the nucleophile like, then we are going to be get that is the this we are going to be get, means which is opposite, which is opposite to the this configuration, means you can find this the groups around the stereogenic carbon is opposite to that of the reactant, this we call as a inversion in configuration. This we can find in both, that is SN1 mechanism and the SN2 mechanism, means it's going to be in the SN1 mechanism the 50%, that is going to be 50-50, means it's going to be formed either inversion configuration, retention configuration as well as, but in SN2 mechanism we are going to be find only inversion in configuration. The product we are going to be get that inversion in configuration.